with linear maps. I consider a special case where we have a linear map from a vector space to its field, and we have this theorem that let L be a linear map from a vector space to its field, then there exists a unique vector in Kn such that L is equal to La, that is, for all x belonging to Kn, L of x is basically equal to A times x. The proof: so we consider the standard basis set E1, E2 up to En be the basis set of Kn. Thus, for x in Kn, we know that x can now be written as a linear combination of these vectors. So I write it as a linear combination of these vectors. And now, if I apply L to this vector x, then this is equal to L of x1 E1 plus and so on xn En. Now, using the linearity of L, I can write this as x1 times L of E1 plus x2 times L of E2 plus and so on xn times L of En. And if I let Ai is equal to L of Ei, then this is x1 A1 plus x2 A2 and plus xn An, which is basically equal to x dot A, which is our required result. And now this theorem also gives us an explicit determination of the vectors of A, that how we are going to compute the components of this vector A. So basically Ai is equal to L of Ei, hence these Ai's arise from basis vectors. And now we can generalize this to general vector spaces. That is, we have a mapping from one vector space to another vector space. So we consider this result now. So we have a theorem that let L be a linear map from one vector space to another vector space. Then there exists a unique A such that L is equal to La, that is, once again, that is, L of x is basically equal to Ax. So we proceed as we did in our previous theorem, that we consider the standard basis of this vector space. So let E1, E2 up to En be the standard column vectors in Kn, and E1, E2 up to Em be the standard column vectors in Km. Now, using these standard column vectors, any vector in this vector space Kn, if I consider x as a vector in Kn, then x can be written as a linear combination of these vectors. Hence, this can be written as x1 e1 plus x2 e2 plus and so on, xn en. And we know that using these coordinate vectors x1, we can write this in this form as well, that this is this vector. For example, if I consider the case of R2, so if in R2 I consider the standard column vectors as 1 0 0 1, then any vector, for example 1 2, can be written as 1 times 1 0 plus 2 times 0 1, which is basically equal to this vector. It arises from these two numbers. So exactly the same case here, that we can write this vector x from these coordinate vector. Now, if I operate L on this vector x, it becomes L of x1 e1 plus and so on xn en. And using the linearity, I can write this as x1 times L of e1 plus x2 times L of e2 plus and so on xn times L of en. Now, we know that this L of e1 is going to be a vector in that L of ei belong to Km, because they are now transformed. And for Km, we have considered these standard column vectors e1, e2 up to em. And hence, all these vectors can be expressed as a linear combination of these vectors. Hence, L of e1, I can write that L of e1 is equal to a11 e1 plus a21 e2 and plus and so on am1 em. Similarly, L of e2 becomes a12 e1 plus a22 e2 plus and so on am2 em. And the last vector can be written as a1n e1 plus and so on a2n e2 and plus and so on amn em. Or further, we can write this as, if I consider L of e1, so using this notation from this one, I can write this as this column vector a11, a21 and am1. Similarly, this vector can be represented as L of e2 is a12, a22, a2n A11, A1n, A2n, and AMN. So L of x basically becomes now x1 times L of E1, which is this one, A11 E1 plus A21 E2 plus and so on, AM1 EM, plus x2 times A12 E1 plus and so on, AM2 EM plus and so on. The last one would be XN A1N E1 and AMN EM, which can further be rearranged as this is equal to A11 X1 plus and so on A1N Xn times E1 plus and so on AM1 X1 plus AMN Xn times EM. And now let A be equal to this matrix, A be equal to Aij, and then we see that L of x is now equal to A times x, and which basically provides us the proof of our required theorem, that this proof, which is that this matrix A is the required matrix associated with this linear map. Thank you.